received, does that mean somebody's going to be left without something?
No.
I mean, if he gives all that he has to me, how's he going to give all that he has to you? How is that possible? So, anybody have questions about sets? Any of the sets that you came across? Did you get into the number sets? The natural numbers, the whole numbers, the integers, etc. Yes?
I just have a question. So I attempted to do like problems 10 through 12, and it didn't really make sense. Like even with reading the introduction that you gave us, I still didn't understand. So if you could go over just how to write that kind of like notation.
Okay.
So
So you're talking about set, ways of expressing a set?
Yes, I think so.
So how many different ways do we have to write a set? 3? What are they?
Set builder notation.
Set builder notation.
A list.
A list.
I forgot.
Description. Which is just an English. Okay. So let's start out with, let's just use one here. Let's start out with the set description saying the multiples of 3 between 10 and 20. There's a description. The multiples of 3 between 10 and 20. Now, if we're going to call that set A, we'll make a list. We always do the set brackets when we do the lists. So what are we talking about? What numbers are we talking about here? 12, 15, 18. That's it, right? Now, so there's a list. This says the very same thing that that says. Except here we've got a list, here we've got a description. Now set builder notation. This is one that some of you may not have been exposed to, or if you have, you find it more challenging than either of these two methods. For this class, I think most of the time on a quiz or a test, I will give you the set builder notation rather than have you interpret it. I'll have you go from here to here or from here to here rather than having you go this way. But let's see if we can do that. So in order to do that, we want to say it's the set of all x's such that what? X is equal to 3n. By multiplying something by 3, that guarantees it's a multiple of 3, right? So x is going to be a multiple of 3 is what we're saying by this. Okay? And what about n? What numbers can I put in for n? So do I say n is between 10 and 20?
Because then that would be 3 times 10.
Because then I would put a 10 in here, and that would be 30. And 30 isn't a multiple of 3 between 10 and 20. So it's got to be between what?
4 and 6.
Between 4 and 6. Is that what you're saying? Okay. Yes?
Can you say X is between 10 and 20?
You could, but if you say X is between 10 and 20, how do we know if it's a multiple of 3 or not? Do you follow what I'm saying? So this part tells us that. So now we're saying that X is a number between, could it include 4?
Yes.
Needs to, right?
Yeah.
Include 6? Yes. Okay, so let n be 5.5. That's not going to work, is it? Well, it's between 4, it fits this description. 5.5 does, right? So what else do I need? I need to say that n is an element of or belongs to the counting numbers, or you could say whole numbers. We could put a W there, right? We could even put an integer, because if it's an integer between there, it will just be 4, 5, and 6, right? But I can't have rational numbers. Do you know what I'm saying? That not any number works between there, just the whole numbers that are.
So what? So I know that's not an E, but what is that like? What does that stand for? That?
It is an element of, or you could say it belongs to. So this n that we're going to put in here belongs to the counting numbers set. So I can't take fractions out of it, in other words.
Okay.
Okay?
And then the first part, the X with the half of the absolute value, and then the next X, what is it?
Such that.
Such that.
Such that. So you probably ought to learn that symbol, such that, and is an element of, to be able to interpret this. Okay? Okay? Does that help a little bit?
A little bit. This is still the first part, like the first half of that, like the X with the X, the such that X. How does that exactly work? Like, I don't understand. Like.
Okay, it's the set of all x's such that.
Okay.
So anything that's an x is in my set, and x is this. What does that mean? What is that telling us?
Oh, okay.
Multiple of 3, because when I put a number in and times it by 3, I get it's a multiple of 3 out. If n is a counting number. Okay? If it's a rational number, then we may not get a multiple of 3 out. And then this tells us, because we only want the ones between 10 and 20, this restricts that.
Okay, so the first part of that is just, those are kind of like two separate things. It's saying that all the x's when x equals 3n. Is that what that's
Yep.
saying? Okay. It was
Yep.
kind of confusing. I just didn't make sure it's straight.
Okay. I don't think we'll get much more complex than that, and I will always give you this and ask you for one of these rather. It's harder to go the other direction. And those of you who are secondary majors need to probably get that experience, but you'll get that in some other courses. Okay, what else about sets? Let me ask this. Which is the biggest set? The set of counting numbers or the set of whole numbers? And if so, why? Which is the biggest? The set of counting numbers or the set of integers? Integers? Everybody know what integers are when we say integers? Have you got a picture in your mind? And then the next question, which is the biggest set? The counting numbers or the rational numbers? Now, why are you saying this? Why are you saying that the integers is bigger than the counting numbers?
Because integers are
So it goes infinite, counting numbers go infinite this way, right?
Right,
But integers go infinite in
both directions.
both directions. Is that what you're saying there?
Yeah.
Because the integers include more in their set than just natural numbers.
What do you mean by more?
Because they include all the negative numbers.
So if they're both infinite sets, then what? You understand what I'm saying? Kind of.
Yeah.
Well, hang on, because we're going to approach the answer to that. If you're given a set, what would you be interested in knowing about that set? What kinds of things might you want to know? Anybody? Frequently, we'll ask, how many? How many elements are in that set? When you ask how many, you're asking for the cardinality of the set. Cardinality means, well, do you remember those numbers that we talked about? 3 ways that numbers are used: nominal to identify, ordinal to give us the order, and cardinal to determine how many. Do you remember that when we talked about those? So when we talk about the cardinality of a set, we're just talking about how many are in the set. That helps you tie those ideas together, I hope. So, what's the cardinality of this set? 3. When I say what's the cardinality, I'm asking how many elements are in the set. There are 3 elements in this set. Okay? All right, here's a set. We'll call it set A. And it's got a bunch of mathematical symbols in it. Does everybody know all of them? Anybody want to ask about any of them? Yeah.
The 4th to the last.
That one?
Yes.
Anybody know that one? Is congruent to, typically referring to geometric figures. Okay. Any others?
No, the one right after that.
The one right after it? What's that? Approximately equal to. It's kind of a wavy equals. So if you've rounded something off, you can indicate that with that symbol. Everybody have all? How about that 8 on its side?
Infinity.
Infinity. Okay. The rest we know? Okay. Now here is the symbolism that we use for cardinality. When you see a little n followed by a capital letter, which is what we always use for our sets, in parentheses, the way we're going to interpret that is cardinality of set A. Okay, so it says find that little n, capital A, that means find the cardinality of A, which means what? What is it? What is the cardinality of A?
12.
12? Why?
That's how many are in the set.
Because there are 12 elements in this set. So, the cardinality of A is 12. Okay? For a minute, what is a number? Well, some people will say, this is a number. Is it? No, that's a numeral. You go, what? This is a symbol that represents an idea, right? What is the idea? Huh?
That there are three.
That there are three. What's three? That's an English word, three. If I were in Spanish, we'd go tres. So, but this symbol, this numeral, your number 3, as we hear it pronounced, and the number tres, is all kind of tied into what? Well, this many of something, right? And you're saying this many, well, we hold up fingers because they're easy, we have them with us, right? Or you could get 3 little stones, or you could get... So what does 3 mean? Have you ever stopped to think about this? I mean, we act like we know everything about this, and yet it's an idea of a certain quantity, right? And we have all jointly decided that if there's 3 stones here, we can go 1, 2, 3, right? And that's 3. But the rocks aren't 3, right? And these fingers aren't 3. It's the idea of that manyness. You understand what I'm saying? And then the Romans, they said, you know, we'll make 3 of these, right? And that's the way they wrote it, right? So it's kind of... By the way, do you know where we got our Indo-Arabic numeral from? Yes? Here's how it was written. They said every angle should be, count for that number. So here's 1. Here's, see there's 1 angle. There's 2 angles. Here's 1, 2, 3. 1, 2, 3, 4. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. What about this next one? How many of you have seen a 7 written like this? How many of you have wondered why it was written that way? Where did you see it written like that? Huh? The way you write it? Where did you get it from?
I don't remember. I've done it since I was little.
Well, I had never seen it before until I went to Spain, and everybody writes it that way because they write their 1s, they still write their 1s like that. And that looks an awful lot like a 7. And I thought, well, they put a little mark on there just to distinguish between the 1 and the 7. No, it's because they need 7. 1, 2, 3, 4, 5, 6, 7. It had a little thing on the bottom as well. Okay, 8, the 4 in the top, and the 4 in the bottom. And over here, how many angles does this have?
None.
Duh. So, okay, and 9? How about 9? Here's 9. A little bit here. 1, 2, 3, 4, 5, 6, 7, 8, 9. That's where the numbers came from, because each angle represented 1 unit. Okay? And now we've stylized them and we've rounded them off, right? Okay. But this idea of number is just it's an idea. It's an abstract idea out there. When I say 5, well, what is that? You say, well, it's that many. But, you know, we think we know a lot about numbers, but it's, okay, so a symbol representing an extract, so the numeral tells us something, and depending on what language you're in, the numeral can be even written differently. And a little later on in our class this semester, we're going to, some people write 3 like that. Computer programmers, that's what they do. That's the binary number 3. Anyway. So is it a symbol or is it the object? Well, it's really not, the number is really not the object or the symbol. It's the symbol represents an idea that's out there, an abstract idea that, okay, there is no all-inclusive definition as number. We just haven't, I mean, we all know what 5 is, but we use symbols and objects to represent that abstract idea that really isn't defined. Okay. How many of you want to be kindergarten teachers? Okay, even if you're not going to be a kindergarten teacher, you're going to be a parent, I hope. I hope. And one of the things parents always do with their kids is teach them. And they'll teach them the numbers, right? So, a really, really important idea for teaching kids numbers is this idea of one-to-one correspondence. How do we start off teaching kids numbers? Huh? Fingers. Okay. Apples. Okay. Counters of some kind. Get them out there, right? Come on, you've helped younger brothers or sisters learn, or nieces or nephews, or anybody have kids in here? Are they old enough to be taught how to count yet? Okay. How do we do it?
There are some books that count things.
We buy them a book, yeah. Like what? Dr. Seuss, doesn't he? He has ABCs. He's got to have it.
Oh, the bear thing. Where
The Berenstain Bears.
No, well,
no?
It's, I think Dr. Seuss. Well, it might be the Berenstain Bears with Dr. Seuss or something. Countings from when I was little.
But we use books. But don't we just start going 1, 2, and we get students. There are our students. We get these kids saying one. We go 1, 2, 3, 4. You know, and then they just start saying it. Do they know what they're saying?
Nope.
No. Then what do? We get them so they can. In fact, I've listened to my grandkids, especially just recently. 1, 2, 3, 4, 7, 8. You know, they know their numbers and they just say them, but they don't know what they're doing, right? They just heard somebody and they're mimicking. Then what do? Somebody said the fingers. We start going 1, 2, 3, right? What are we doing when we do that? Or when you use the apples, if we grab and we start saying 1, 2, kindergartners will get out their counters, little plastic bears or plastic what? What did you use in your kindergarten? Blocks, okay, blocks, counters. And what we start doing is we give the name of that number, the name, notice, remember it's just an abstract idea anyway. This particular symbol means this many objects, right? So we'll go 1, 2, 3. And what we do when we count and teach them how to count is we make a one-to-one correspondence between the numbers, specifically the counting numbers, that's why we call them the counting numbers, and some object. So when I say 1, it goes with this. When I say 2, it goes with this. When I say 3, in fact, I dare say that, let's go back here to, when we found the cardinality of set A, what did all of you do? Is there there's one. You probably went like this. You started right here and went 1, 2, 3, right? All of you? Yes? What did you just do? You made a one-to-one correspondence between these symbols and the counting numbers. So what do I mean by one-to-one correspondence? Here's another set A. If we want the cardinality of set A, what do? We take the set of counting numbers and we make a one-to-one correspondence. That one corresponds to that, that one corresponds to that, that one, that one, that one, that one, that one, and that one. And therefore we say there are 8 items in that set. The cardinality of set A is 8. Why? Because we can make a one-to-one correspondence with the counting numbers and set A. Now, if I match up the set of counting numbers with every one of these in a one-to-one correspondence, then however many counting numbers I match with, we would say that that's how many are in the set. Does that make sense? You're making a very simple idea too complex. Well, that's how we do it. Now, how do we tell if 2 sets are the same size or not? Anybody want to answer that?
Can you re-ask that? I don't think I understand.
How can we tell if 2 sets are the same size?
Besides
Both
counting?
correspond to the same number?
You what?
They both correspond to the same number?
They both correspond to the same number. What do you mean the same number?
Like how you set this up where like 1 corresponded to that exclamation point, 2 corresponded to that.
Okay. So we would say set A and set B are the same size. Everybody, right?
Right.
By the way, if 2 sets are the same size, that means they have the same cardinality. And if they have the same cardinality, we say they are equivalent. We don't say they're equal. We say they're equivalent. And that's a little bit different than our idea. A lot of us think of equivalent and equal being the same. But with sets, are A and B the same sets?
No.
Then they are not equal sets. Equal sets are sets that, except for the order, they contain the very same thing. So if I had A being 1, 2, 3, and B being 2, 3, 1, A and B are, we would say A is equal to B. The order doesn't matter. As long as they contain the same elements, they're equal. But to be equivalent, they don't have to have the same things in them. The cardinality of A is equal to the cardinality of B, so we say A is equivalent to B. And that little symbol there is the way we're going to write equivalent. It's a 1 little squiggly. Yes?
When you said that they were in the same element, I got confused. What do you mean by that?
Wait a minute.
Yes.
I thought A and B were different. I thought A said A had something else in it. 1, 2, 3. There we go.
Okay.
Now let's get rid of this, because that doesn't make any sense anymore either. There we go. If A is 1, 2, 3, no wonder you were mixed up. If A is 1, 2, and 3, and B is 2, 3, 1, we say they're equal sets.
So as long as they have the same numbers in them, it doesn't matter.
They have the very same elements. They don't have to be numbers.
It could be any.
As long as the elements in them are the same, they're equal
It
sets.
doesn't matter the order, just as long
If
as
they have the same number of things in them, they are equivalent sets. So every pair of sets that are equal are also equivalent, because if they have the very same elements, they will have the same number of elements.
Okay, so for with equal sets,
1, 2, 3, and 4, then wouldn't, and.
So if C was 1, 2, 3, and 4,
And C and B would not be equal, right?
neither would C and A, right? They're not equal sets.
They have to have the exact same thing, it just doesn't matter what order they're in.
Correct. Now, what if I did this? What if I said C is 2, 3, and 4? Are they equal now? But they are equivalent. So I could say the cardinality of B is equal to the cardinality of C, right? And if I can say that, then guess what I can say? B is equivalent to C. Does that make sense?
Can you write that notation with 3 sets, or is it just one, like a pair of sets?
You can just like I can do 1 plus 2 equals 3 equals 4 minus 1. Yeah, I can keep stringing them on because these are numbers. So I can keep putting equals. I could say this is equivalent to this, and if C is equivalent to something else, I could put it. Yeah.
So if you were to put on another one, you would just put like equivalent to D, which is
I could put
4, 5,
A.
and 6.
Okay.
Right here.
Oh, okay.
Yep, we could do that. Question?
So A, B, and C are equivalent because of the 2 and 3 that are in all of the sets?
No, it's because I can make a one-to-one correspondence between them. I can say that matches with that matches with that, and that matches with that. And if I can make a one-to-one correspondence, then their cardinality is equivalent, and therefore they are all the same size. That's why I can do it. Okay? So what makes 2 sets equal?
The same elements in the set, but they don't have to be the same order.
The same elements, but not necessarily the same order. They could be, but they don't have to be. Okay? If I've got finite sets, that's an easy thing to do. We just observe and we look at them. Even if they're big sets, we could, spend the time and compare all the elements in the one with all the elements in the other one. Okay? What about infinite sets? Well, if I have 2 finite sets, everybody know what finite means? What's define finite? The end.
Like a set.
A set?
No, like permanent. It's, I don't know. It's
finite?
They have a
not
definite
changeable.
number of.
They're countable, right?
Countable.
I can actually count them and it ends.
Throw it
All
up
right?
there.
Finite. Infinite means they go on forever. Now, we gave you some sets in the homework last night. The counting number set. Is it finite or infinite? The counting number set.
Infinite.
Infinite. Why?
Goes on.
Where does it start? 1, 2, 3, 4. Where does it end? It doesn't. So it's an infinite set. Same with the whole numbers. Now I asked the question earlier. Which is bigger, the set of counting numbers or the set of whole numbers? And you say, well, you can't count either one. Right? Because they're both infinite. Well, do you have to be able to count and know how many are in a set in order to tell if they're the same cardinality? Let's just do this. Let's go over to the BYU Idaho Center in our mind. If we go to the BYU Idaho Center, there's, I don't know how many seats are there. They've given that it's 6,000, is it? Something like that. But let's just say I walk into the BYU Idaho Center and I look, and every single seat has a person sitting in it. Do I need to know how many seats there are and how many people there are to know that the set of people and the set of seats have the same cardinality? Why? Because if a person is sitting in every seat, there is a one-to-one correspondence between the seats and the people. And I don't need to know how many are there to know that they match up in that one-to-one correspondence, and therefore their cardinalities are the same. Does that make sense? Yes.
It's 15,000.
15,000.
I don't know. It says BYU Idaho Center.
Oh,
A
yes.
seat
What was I
containing a
thinking?
15,000 seat auditorium.
15,000. It is 15. Where'd I get 6? I know. That was what the, I think that's probably the part. And back when I was in Ricks College, that was kind of our upper limit. That's where it came from. All right, so watch this. Here is the set called counting numbers. By the way, N stands for what?
Natural.
Natural numbers. Sometimes we call it the counting number set, sometimes we call it the natural number set. Very same set. Why would we give the same set the different names? I didn't do it. I'm just teaching you. Okay? 1, 2, 3, 4, ... The whole numbers is 0, 1, 2, 3, ... Now watch. I'm going to match 1 with 0, 2 with 1, 3 with 2, 4 with 3, and I'm going to continue to match. Can I go forever matching this way? And therefore I've established a one-to-one correspondence between the elements of the natural numbers and the elements of the whole numbers. Therefore we say what? The cardinality of the natural numbers is the exact same as the cardinality of the whole numbers, which means they have the same size infinity. Question, comment?
You cheated. Yeah, wouldn't the whole numbers like have more numbers in it because you do have the 0, and so you're matching the 0 up with the 1?
You're asking about which set?
Like the whole numbers. Like earlier you asked if...
Which one's the biggest?
Yeah, which one's bigger? So wouldn't the whole numbers be bigger because it has the 0 in it? Because then your
You
sample...
might think that right at first. But if the idea of bigger than means has more elements than, I just proved that I can make a perfect one-to-one correspondence between these two sets. It's like saying, I don't know how many people are in the BYU Idaho Center, and I don't know how many seats are there, but I know there's a one-to-one correspondence, therefore they're the very same size. I just showed that very same thing here. These are the same size.
So what's the difference between like the same size and equivalent? Like,
Equivalent means they have the same cardinality,
okay.
which means they have the same number of elements. It's the thing that makes this difficult, it's using what? Infinite size sets. All right, let's go to the next one. What about the integers? Is the integer set, is it bigger than the counting set? Somebody said, oh, it goes infinitely in both directions. So when I put the integers, and what letter did we give you? Z. Does everybody know where that came from? I don't know why they did it, but the German letter for integer starts with Z, and that's where it came from. Anyway, it goes like this. ... -3, -2, -1, 0, 1, 2, 3, ... right? And right off the bat we say, oh, this has got to be bigger because if I match these up here with this, right, there would be all these left over. But watch. What if I match 1 with 0, 2 with 1, 3 with -1, 4 with 2, 5 with -2, 6 with 3, 7 with -3. Could I go on matching them one to one so that every element in the natural numbers got matched with exactly one element in the, yes? Therefore, they have the same cardinality. Why? Because I can make a one-to-one correspondence with everything in here with everything in there. Does that make sense? Now, what about the natural numbers? And the rational numbers. What's a rational number? Any number that can be written as a fraction. So is this a rational number? Yes, because I can write it as 16 over 2, or I can write it as even 8 over 1, or whatever. Okay, any number that can be written as a fraction of integers. So if I have this, is that a rational number? Yes, because I could write that as negative 2 over 1, or 2 over negative 1, right? Those are the same thing as, okay, any number that can be written as a, by the way, the word rational comes from the word ratio, and ratios can be written in several ways. 2 to 3. How else have you seen ratios written? 2 to 3 with a colon. Have you seen it written that way? And 2 to 3. And this is the one we want to think about. Fraction, ratio, rational. Okay, so anything that can be written in. So now, how many rational numbers are there between 0 and 1? There's a half, right? And a fourth, and there's a 3/4, and a third, and 2/3, and how many rational numbers are there between 0 and 1? Infinite. Right? So now the question might be asked, which is bigger? The counting numbers or the rational numbers? And you're saying, well, wait a minute. The rational not only includes the positives, it includes the negatives, and it goes infinite in both directions. And now we're saying that between any two counting numbers, there are, so there's an infinite number between 0 and 1. There's an infinite number of rational numbers between 1 and 2. So now we've got infinity going to the inside as well as here. So the question is which one's bigger? Well, the question remains. To be able to tell if they're the same or one's bigger than the other, what do we have to do? If we can make a one-to-one correspondence between the counting numbers and the rational numbers and show that every single counting number gets matched with every single rational number, then we could prove they're the same cardinality, they're the same size. If we can't, then they may not be, right? Some of you are saying, what does this have to do with anything? Well, I think it has an awful lot to do with the questions we asked. Count your many blessings, name them one by one, you know, this. What are you doing? You're making a one-to-one correspondence as you're doing those counting of the blessings, right? And this idea that God has promised everyone who is faithful what?
All that He has.
All that He has. How is it possible that all of His children can have all that He has, all at the same time? That means He wouldn't have anything left, right? No. So, your job, one of your jobs is to be thinking about, could I make a one-to-one correspondence between the counting numbers and the fractions, the rational numbers? Is it possible? So far, we've said that these two are the same size, and these two are the same size, which means these two are, right? But are the rational numbers? What letter do we use for those? Q. Everybody know why we use Q? Because when we write it as a fraction, one of the meanings of a fraction bar is what? Divide. So it's the quotient. Yeah. That's why we use the Q there. All right. I believe you've got... Now, here's another good question. How could an infinite atonement, what does infinite mean? Covers every person. Not only does it cover every person, it covers
Everything.
every sin that every person covers. Not only does that, but it's Brigham Young taught that Christ underwent the atonement for all the people that have lived. That's going back into time, and all the people that will live. Right? That's infinite in two directions. Right? And we know from the Doctrine and Covenants that this isn't the only planet that has people. And Brigham Young said the atonement that took place on this planet covers those people as well. Can you think? So, Christ was in the garden only a finite amount of time. How could that finite amount of time do or effectuate an atonement that is infinite in time, in space, in... We hope by the time we're done with this unit, you can have some better answers to that question. We'll see you on Friday.